Okay, question 3 from the 2014 Level 3 Waves paper. This is on the Doppler Effect. This is a pretty cool question. The tourist is watching a ferry boat come towards her. The speed of the ferry is 5.50 metres per second. Again, they're sticking with those three significant figures. The ferry sounds its horn, producing a note of frequency 95.0 Hz, and the speed of sound in air over the water is 3. This equates to 350 metres per second. Okay, just going to scroll down. I'll give you a lot of space there, but the very first question is to calculate the frequency of the note that the tourist hears. So we're using our standard formula here for the Doppler effect, Vs over VW, should know this, over VW plus or minus Vs. So we're plugging in the velocity of the wave, the velocity of the source, and our frequency. We just have to work out whether we're going to plus or minus when we put it in. Now, when it's coming towards, you're going to hear a higher pitch. The racing car starts higher pitch and goes lower. So it's going to provide a higher, so F dash is going to be higher than F. For that to happen, everything in this bracket here must be greater than 1. Okay, if it's greater than 1, then you're multiplying something greater than 1 by F to get F dash, which is greater than F. So it makes sense. For that to be greater than 1, the top has to be greater than the bottom, so it's going to be minus. Okay, so VW minus Vs. Plug those numbers in, do your calculation, you'll get an answer. B, explain why the sound of the horn is heard by the tourist, where are we? Doesn't have the same pitch as the sound emitted by the horn. So this is a question asking you to explain the Doppler effect. Okay, explain the Doppler effect. And the way you're going to do that is by talking about the moving source causing the waves to bunch up at the front and to spread out at the back. So as the source is moving in this direction, and how that occurs because a wave is released, the source moves closer to where that wave is than if it was stationary, and it releases a wave front here rather than here, so that you end up with a bunching effect in the direction of the motion. And you can explain that in as much detail as you need. That shortened wavelength results a higher pitch or higher frequency. Moving on up. Same diagram here, except with the second boat. Second ferry, which is overtaking the first, also sounds its horn, producing a note of frequency 90.0 Hz. For a few moments, both ferries are the same distance from the tourist, quite close together. Both are sounding their horns. The tourist hears beats. Calculate the frequency of the beats that is heard by the tourist. Okay, this gives you a little bit of space. So what you're going to have to do is use two formulas. Your beat frequency is going to be F1 minus F2. Doesn't really matter which one F1 and F2 is. You could put the absolute value brackets there to identify that your final answer is going to be positive no matter what, and just subtract the two different frequencies from each other. Okay, so for the first one, I think we've already calculated the F dash value for that by the tourist. So F dash for boat A, or boat 1 if you want, in which case you can have frequency A and frequency B, dash dash. Anyway, for the second one, it's coming towards you again, so you're going to have to do the same calculation. So F dash for boat B is going to be equal to F of boat B, which is 90 Hz, times by velocity of the wave, over velocity of the wave minus, again because it's coming towards the observer, minus the velocity of the source. So you can do that calculation, find an answer for that, throw it into there, take the answer from up above and throw it into there as well, and that'll give you the beat frequency. Okay, the next question, very typical, and the last one, last one in the paper. Describe what beats are. So what beats are, and explain how they're created. So two things, describe and explain. When you're describing, that's what you would hear. Okay, and you're not going to hear the frequency as a note. what they're wanting you to describe is the increase and decrease of volume at the frequency of the beat in there. So again, I'm not going to get into the technical details, but the beat frequency, part of the explanation of how they're created is that they have to be close together in frequency, so two frequencies close together, and if they are, if the difference is too small, you can't actually hear a note anyway. It would be like, say if you had a beat frequency of 2 hertz, you're going to hear a louder volume twice a second. So, you know, think about something vibrating at twice a second. That's not going to give you a note, so to speak. Even if you watched a speaker doing that, you would see the speaker cone coming in and out twice every second. And that's not going to produce a note. It's going to produce a change in volume when you've got the other frequencies overlaid over the top of that. Explanation of how they're created is that at the beat frequency they'll constructively interfere, and you describe that constructive interference to produce twice the amplitude, and then less, and then twice, and then less, and then twice. But yeah, you see where that's going. I think that gives you enough to work out where to go from there. So that's the end of the 2015 Waves Level 3 paper.